Okay, good morning, everybody. Good afternoon for some. Uh, Welcome to another Telops webinar, and thank you for joining us. My name is Chris Giesecke. I am a field application scientist with Telops. I will be acting as your host, your pilot for today. I am very excited to have with us also our guest speaker, Dr. Miguel Valero. Um, First things first, I want to get a few housekeeping things out of the way. And Uh, we'll start with, I just want to let everybody know that this webinar is being recorded and that we will provide the recording of the webinar and a follow-up email after the webinar ends. We also encourage everybody to put in any questions that they have, any questions from the audience. If you hear something during the webinar that piques your interest or anything you'd like to hear some more about, please feel free to use the GoToWebinar questions tab over here during the webinar, and we'll reserve about 15 minutes after the webinar is over to try and answer some questions live. And then any questions we're not able to get to, or all of the questions, we'll provide also in the follow-up email in written answer format. Okay, so once the webinar is over, we'll do a follow-up email that will give everybody the link to the recording of the webinar along with the questions, written answers to all of the questions. Okay, so the first thing we like to do with our Telops webinars is we like to take a poll just to kind of see where everybody is in regards to infrared imaging and kind of what your background is on it. So let me launch this poll here real quick. Okay, and the poll is, how would you rate your knowledge of infrared imaging technology? Okay, everybody should see that pop up. If you could, let's take 30 seconds to a minute here to answer some of the questions, to answer the poll, and then we'll just kind of go over to get a rough idea of where everybody in the audience sits. Okay, I think that's about enough time here. I'm going to end the poll, and we'll just take a quick look at the results. So it looks like for the most part, we've got a pretty decent distribution here. About 28% of you with no direct experience but are interested in the technology. Some of you have no direct experience but have considered this technology before. The majority of you have direct experience with collecting or analyzing infrared data, and then some of you are thermal imaging experts. So it's always good to have a good spread in the audience there. Okay, I will close the poll out and make sure this works. Okay, everything's set up, and then we can go ahead and get started here today. Just make sure that works. Okay, so today's webinar is infrared imaging and fire behavior. Okay, we're very excited to do this. Again, I'm very excited to have along with us our guest presenter today, Dr. Miguel Valero. A few quick overview of our outline for the day. is I'll first start with an introduction of Telops, an introduction of the applications that our cameras are used for, and then I'll do a little bit of a background in infrared imaging and wildland fire, just for those of you who aren't too familiar with it or don't have the direct experience in it, just to give you a little bit of a base knowledge. And then after I finish doing that, I will turn it over to Miguel, and he'll give his presentation. Again, we'll allow 15 minutes afterwards for questions and answers, and then and then we'll finish up by concluding and giving you guys one last rundown of what to expect afterwards. All right, so Telops. Telops was started in 2000 in Quebec City, Canada. We design and manufacture high-performance, hyperspectral, and infrared imaging systems for defense, industrial, academic, and research applications. Like I said, it was started in 2000, now employs over 100 people, mostly scientists and researchers. So we like to bring that science background into the cameras that we develop and the support that we have for our clients. We have established itself as a world leader in thermal infrared imaging solutions, and several years ago we became part of the Exosens group. We now offer innovative solutions for aerial methane leak detection and quantification. If you can see, that is this image down here on the right is an image for methane leak detection. We recently have also acquired LR Tech, in which case you'll hear just a little bit about them today, one of their products today as well. Okay, some of the products that Telops offers. We'll start here on the left with our hyperspectral cameras. These are high spectral resolution. What you'll get is within the calibrated wavelength range that the camera is capable of recording measurements in. Each one of those pixels will give you a full range of that particular spectrum. So doing things...
I'm sorry, Chris, sorry to interrupt, but I am not seeing the images you're showing. I don't know if everyone else can. I'm stuck at your webinar outline.
Let's see. If that's the case, it looks like it's showing up on the... Sorry, pardon that, guys.
Apologies if it's just me. Didn't mean to interrupt.
Okay. Yeah, no problem. Let's see. It shows that I'm sharing my screen, and I see it as being on the Telops products page. I can check in to see if it's okay. I got one thumbs up that they're able to see my screen. So everybody right now should be seeing the Telops product cooled air cameras. Are you able to see that now, Miguel?
Still not, but I know it already, so
okay.
Apologies for the interruption. Go ahead.
Okay. All right, so those are our hyperspectral imagers. Again, they allow us to do things like identify gases or minerals and quantify those. Next are our multispectral cameras. Okay, this also is great for spectral resolution, time-resolved multi-channel imaging. We'll talk a little bit about the multispectral camera today. Then we, of course, have our high-performance fast cameras. Okay, our cameras will either focus on spatial resolution, temporal resolution, or spectral resolution. Our fast cameras focus a little bit more on temporal resolution, so you get really high frame rates and in full windows of operation. You get frame rates of a couple thousand. In the sub window, you'll be able to achieve frame rates of 60, 80, 100,000 for our fastest camera. And then we have a couple of other new exciting cameras, and the first one being the high dynamic range camera. We're very excited about this. This is new technology that's out there. And this camera allows you to see a dynamic range in a scene at a single exposure time of up to about 900 degrees Celsius. That is quite the range. You typically see about maybe a third of that with a regular midwave camera. So really excited about that. There'll be a brief part on that as well. And then our new entry level cameras, the Radia. Okay, these are nice because it's good high resolution, but they're very compact and very mobile. So if you need somewhere to fit in tight spaces, then the Radia is a good camera to consider. These are some of our main applications that our cameras are used for. Ballistics, combustion, IR signature, gas detection, cold spray, experimental mechanics, additive manufacturing, non-destructive testing, mineral identification, and of course, like we'll be talking about today, fire research. So a little bit of a background here. If we take a look at this figure on the left, okay, these are black body radiation curves, different temperatures. Let me see if I can bring up the laser pointer here. If you guys can see this. So for reference, the black body radiation curve of Earth's temperature, about 300 Kelvin. Okay, we take that as like an ambient temperature in a sense. And then way at the top here, we have the sun's black body radiation curve for the sun's temperature, about 6,000 Kelvin. So typical for wildland fires, you will see about 1,000 degrees Kelvin. Of course, the range is different depending upon the intensity of the fire. You might have it down to 700 Kelvin or as high as like 16 or 1700 Kelvin for a really intense burning fire. But usually we can consider it to sit the temperature of a fire to sit around 1,000 Kelvin. And so with this, we're able to identify the signatures that are left or output by a wildland fire. And we can say that, okay, typically this wildland fire will be visible in the visible part of the spectrum, the short, the near, the mid-wave, and the long-wave part of the infrared spectrum. That allows us to understand where we want to and how we want to observe wildland fire. A couple things that need to be considered, of course, smoke is a big one, reflectance of other surfaces such as the sun. So when we look at, say, the visible is great to see fire, but as soon as there's a little bit of smoke, that can completely obscure your image. And the shortwave is great because it has some transmissivity through smoke and it's able to catch the really hot parts of the fire. But once the smoke gets a little heavier, then that too can also become obscured by smoke. So we like to focus a lot on the midwave and the long-wave infrared. The midwave allows us to still capture those higher temperature portions of the fire and the more intense aspects of the fire. And then the long wave allows us to capture kind of the lower temperatures and stuff that's closer to ambient. And you can use the two to kind of work off of each other when you're trying to analyze things. And then we also need to take into consideration that there are other things happening within fire, within combustion, and that is the products that are produced from the combustion process itself. Things like water, water vapor, CO2, carbon dioxide. And so sometimes you need a higher spectral resolution. So you need multiple sensors or multiple filters in order to observe some of those different things. And we'll talk a brief about that coming up here. Okay, so we have our infrared cameras, and if we're looking at something, we want to prioritize spatial resolution over frame rate. You don't necessarily need high frame rates to observe wildland fire movement or fire behavior. So spatial resolution might be a focus for you, in which case you would look for cameras that have larger detector rays and smaller pixel pitches. This will allow you to achieve that higher spatial resolution. And you can still bump the frame rates up to about 100 hertz or so if you need to. But for Telops, these would be cameras like our HD series cameras or high definition series cameras, the M350, the M100 for midwave, and then for long wave, the V500. Those are all good resolution with frame rates that are still achievable for what you're trying to do. Also, maybe the focus is now towards the dynamic range. That's something you need in a camera. This is something, since it's new, I think it would be of great use for wildland fires. And this, again, would allow you to see a really large dynamic range of temperatures within a single exposure time. So the image that we have here, down here, is using a blowtorch. So you notice that you can see the flame, you can see the products of that flame, you can also see the workbench that it's on, and you can see the person in the background. So it's possible that a high dynamic range camera like this might allow you to see the background and those higher temperatures of the fire, maybe for something that's not burning crazily intense, but it would be very interesting. But high dynamic range is something that could be very useful in wildland fire research or for fire applications. And then next, if spectral resolution is something that you're looking for, our multispectral camera, okay, this comes with an 8 filter rotating filter wheel, so you can simultaneously capture different filters of the same scene, images from different filters of the same scene. This little plot here on the left kind of shows you within the midwave infrared part of the spectrum some of those combustion products that you typically get. Okay, hydrocarbons, carbon dioxide, carbon monoxide, and water. And so using this, we're able to identify the spikes or where those spikes typically occur within that part of the spectrum. And so you can use different filters. You can input different filters into a multispectral camera in order to obtain images of those specific wavelengths. So if we look here, the image on the right, okay, this is of a burning pallet, a fire of a burning pallet that was taken with some of our good friends at WPI. And we can see here that you'll achieve an image that produces eight of the filters observing the same scene. And we have listed here the different, what the different filter wheels are looking at. So this first filter wheel is just a broadband, so you're just observing the whole image, no specific wavelength filter there per se. So you see the full intensity of the fire itself. Filter wheel 2 would be an optical density filter, so you'll see a little bit less intensity since that's filtering out intensity. And after that, this particular filter is observing only the H2O in the scene right here. So you're not going to see as much, but this will show you the water content that you're looking at. And then these next two on the bottom here are carbon dioxide filters. They are separated into red spike and blue spike, the red spike being higher energy, so you're going to see a lot more intensity there. And then a through flame filter. So looking at these combustion products on the plot on the left, we can see there is a spot where you can actually see through the flame. You're essentially seeing through the combustion products. So that allows you to see what's going on underneath or through those particular products and just looking at that burning surface itself. And then hydrocarbons. So it's really cool what we can be able to do. You can also use this camera just to observe the scene on a single filter if that's all you need. So it's got kind of a dual purpose here. But these come with standard combustion filter wheels that we have for several different occasions depending on what you want to do, or you can customize them. But if spectral resolution is very important to you and you want to observe, say, the different breakdowns of the fire and of the flame, the dynamics, and the combustion products itself, then this is something that you'd want to consider or something that could be valuable to you. Next is a product. This is the Assist 2. It's an atmospheric sounder. Okay, this comes to us from LR Tech, the company that just recently joined us. And this is for atmospheric profiling, and it could also be used for fire weather. Atmospheric soundings. So this provides basically a bottom-up approach to atmospheric soundings, and they play a key role for researchers. Allows you to measure crucial atmospheric variables. Satellites look at it from the top down. This particular instrument looks at it from the bottom up. And so things like weather balloons, atmospheric sounding instruments as the assist here can help with not only accurately reading the lower part of the atmosphere, but validating satellite sensors as well. So this allows us to measure properties such as aerosols, simple clouds, mixing ratios of trace gases, and the vertical distribution of temperature and vapor. This is looking up to about 600 millibars, roughly 600 millibars, so about 4 kilometers up towards the into the atmosphere. And so we offer this infrared spectroradiometer that can provide high spectral radiance or spectral radiance over a broad spectral range with high spectral and temporal resolutions to help fill kind of those boundary layer gaps that you that are kind of tough to read within the lower parts of the atmosphere, closer to the surface. For fire weather, this sort of instrument can provide accurate assessments for atmospheric profiles closer to the surface with temperature, humidity readings, and some mixing ratios of trace gases there. These also help to track long-term changes in temperature and humidity profiles and short-term temperature events, which is extremely important in understanding not only the atmosphere, but long-term climate changes. This instrument has been used several occasions. The National Weather Service has worked quite a bit with it. We're excited to introduce this, into the Telops product line. And these ground-based technologies, they're great at helping validate satellite instruments and provide some long-term observations as well. So we're excited, and these could be very interesting for fire weather applications as well. Okay, so that's enough for my introduction for Telops and infrared imaging using Wildfire for wildfire applications. Now, what I'd like to do is I'm going to turn this over to Dr. Miguel Valero. I'll give him a brief introduction here. Dr. Valero is an associate professor at the Universitat Politècnica de Catalunya in Barcelona and an adjunct research associate with the Wildfire Interdisciplinary Research Center at San Jose State. His research focuses on wildfire dynamics, its observation through remote sensing, and the improvement of existing models leveraging data. Dr. Valero and his team collaborate internationally with fellow researchers, industry partners, fire managers, not only to generate and disseminate knowledge, but also to translate it into actionable results. So I'm going to give him some control here. Let me see. And okay, I'm going to allow Miguel to become the presenter, and you should be able to share your screen and present, Miguel.
Okay, let me see if I can figure this out. There you go.
Cool.
Thanks, Chris. So hopefully you can see my screen, my presentation.
Yep, we can see it. And oh yeah, just to let you guys know, I had the privilege of working with Miguel as my advisor during my time at San Jose State, which was excellent, and the stuff we did was really cool. So excited for everybody to hear it.
Thanks, Chris. Thanks for that wonderful introduction and the whole overview of Telops cameras and how to use them for fire research. I certainly think there's a lot of potential here. We've been already exploring some of it, but it's just amazing how fast technology is moving forward and what opportunities that brings. And now that you mentioned it, the first thing I want to do is acknowledge all the contributors that have made possible the research that I'm going to talk about. So I'm presenting it, but there's there's a whole team that have worked on it during the past years. Chris is among them. Um, and you can see the team is divided between San Jose State and UPC in Barcelona. And before I move forward to talk in more detail about infrared imaging and remote sensing of wildfire behavior in general, assuming that maybe the audience today doesn't necessarily aren't necessarily experts in wildfire, I want to also give a brief overview of why we're doing this and why this is important. And many of you are probably aware that wildfire is a problem, although I may discuss that a little more later on. But we have a problem with wildfire. So society has a problem with wildfire because we are suffering the impact of wildfire, and you can see a clear example here of the California wildfires in 2018. But the same um, similar episodes have happened around the world. I'm talking to you right now from Spain, and this summer is terrible in terms of wildfire. As we speak, there are tens of large wildfires burning throughout Spain. There are a lot of people um, evacuated and really large impacts and losses of property. And that has happened throughout the globe, right? Like all continents have been affected recently by wildfire. And it's a problem that's not going anywhere. It's here to stay. And science predictions and climate predictions say that we should get ready to continue dealing with this in the upcoming years. Well, it's not just climate predictions and climate models that say it, but also the evidence is starting to say that the problem is getting worse. So it's not only gonna stay with us, but the impacts of wildfire are growing, and you can see here the amount of money that costs in California, and the amount of the size of the areas that are burned yearly. And similar graphs could be produced in many other places, again, in the world. On top of that, the problem is not just that there's more fire, there's larger fire seasons, more days with high fire danger. It's also that we are seeing more and more extreme fire behavior. We're seeing more and more intense fires, fires that get out of control more frequently, and phenomena that we don't really know how to deal with. You have a couple of examples here, for example, of pyrocumulonimbus. There's been a lot of research lately on pyro-CVs and how they are formed and what factors affect their formation and how they develop, etc. Right? There's a lot of physics, very complex physics here that we don't completely understand. And that's where I want to get with this introduction. Fire itself is not necessarily a problem. Fire, specifically natural fires and wildfires, have always been in the ecosystem, and they are an essential part of the natural ecosystem. The problem, it is a problem that we as a society have with wildfire. And there are a lot of reasons for that. Climate change contributes to it certainly, because we're having drier summers, hotter, more extreme weather events. But there are other factors that come into play, like land abandonment, the lack of land management, also fire management itself for decades, because society has been afraid and has suffered the effects of fire for decades. We've tended to suppress all fire systematically and very, very aggressively. And that, paradoxically, that has produced a bigger problem where if we don't let the landscape burn as it used to naturally, we are just keeping vegetation from burning, and we're producing the accumulation of vegetation that will later on burn at some point. And when it does, if we haven't managed the land properly and we haven't allowed the natural fire cycle to happen, that's where we get all those extreme phenomena. And so my main point with this introduction is we need to know, we used to know uh, um, like centuries ago how to live with fire. It seems like we're kind of forgetting how to do it, and so we really need to learn or to know how to live with fire in the ecosystem and how to manage it and reduce and minimize the bad impacts of fire, but keeping it in the ecosystem. And in order to do that, we need knowledge, right? We can't manage something that we don't know, and that's where all this research in fire dynamics comes in, right? Because we do have a basic knowledge of fire and fire behavior and how fire behavior relates to other factors like terrain, weather, etc. Right? But a lot of times that knowledge is qualitative, um, or derived from experience. And when it comes down to producing numbers, like for example, here in this slide, you have an example of, okay, how large does my protection zone have to be around my home so that it doesn't burn if there's a wildfire? When it comes to generating those numbers and those quantitative measures, that's where we don't have all the knowledge we need yet, because that kind of applications rely on models. And there are a lot of models out there. I'm going to show you a couple of examples from collaborators. There are a lot of models that, for example, this is a very large scale model that resolves the coupling between fire behavior and atmospheric behavior, atmospheric dynamics. We have very large scale models like this that can predict where the fire is going to go and how it is going to interact with the atmosphere. We also have smaller scale models, or we need smaller scale models, and there are people working on it, in this case from the US Forest Service. We need these models to tell us what difference may it make treating the vegetation in a different way. So depending on how much thinning I do or how much vegetation I remove from a certain place, how is that going to affect the fire behavior? That's useful, for example, to reduce the fire risk around my house, right? In order to be safe, how much vegetation do I need to remove, or do the authorities need to remove? So there are a lot of people, a lot of research working, a lot of people working on these topics. The problem is this is an extremely complex set of phenomena. It's not even just a phenomenon. It's a set of phenomena that takes place across many different scales, and it's incredibly difficult to resolve. And so when you go to scientific studies, and these papers are a little dated, but this still holds today. When you analyze the output of all these models, there are a lot of different models that produce a very broad range of outputs, right? And they don't always get it right because there are very large uncertainties, and it's really hard to deal with them and narrow them down. It's not that the models are wrong. Well, I mean, there's a saying, right, that all models are wrong, some of them are useful. So this is a very good example of that, because it's really hard to capture everything that we need. So we really need to make sure that we are capturing what we need, that we're capturing it right. And in order to do that, we have the fire science community, the wildfire science community has a very big problem from my point of view. And it's the lack of data, lack of observational data. If you think about other phenomena, about other problems, if you come from engineering, well, if I ask you to produce a model of something, what's the first thing you're going to do? You're probably going to go to the lab or to your testing facility, and you're going to gather some data and then come up with a model, right? It's really hard to produce models with no data. Well, that's a challenge we've had in wildfire science for a long time, for obvious reasons, right? Because it's not, if you want to study wildfire, you can't just walk into wildfire with a thermocouple and measure temperatures, right? It's really hard to collect those data. And as I said, we know the general relationships between all the phenomena that plays a role in wildfire behavior. So we know there are relationships between the fire, the fuels, meteorology, terrain. We know that at the lower scales, there are a lot of phenomena that we know and we can resolve, like combustion, pyrolysis, heat transfer, turbulence, etc. Right? But we don't have complete integrated data sets of everything at the same time and at the scales that we need. And that's where remote sensing, including thermal IR imaging, is, from my point of view, revolutionizing. It's revolutionizing this because it's providing the means and the opportunity to measure quantitatively a lot of these phenomena that it has been very hard to observe by other means. And these opportunities have facilitated, have enabled the planning and the design of a lot of big field campaigns to study fire behavior. You have a few examples here. That figure comes from the FASME project, which is one we're tightly involved in, led by the U.S. Forest Service. We've also collaborated with other partners, other agencies in efforts like this. We've worked with CAL FIRE, for example. I'll show some data we collected with them later on. We've collaborated with NOAA, the National Oceanic and Atmospheric Administration from the US, that has also conducted the CAL FIRE experiment in 2022, for example. NASA has also launched the FireSense campaign that's ongoing. So all this technology is enabling a lot of new research with a great potential, right? In Europe, so you'll see a lot of our work is based on the US, but also there's a big fire science ecosystem in Europe. There's the European Network on Extreme Fire Behavior, for example. There are also people organizing field experiments. So there's also a very good ecosystem in Europe, and I know in other places as well, like Canada, Australia, South America, Asia, etc. There are similar associations and networks. So specifically, getting down to a little more detail on IR imaging and how we use Telops cameras and that kind of sensors to study fire. Well, this is a system that we built. This is our wildfire imaging system that we call SWISS with one S. And it's a multispectral infrared imager designed to observe fire behavior. It's multispectral, as Chris said in the introduction. We're interested in the mid-wave and long-wave infrared ranges because that's what allows us to quantify the heat, the energy radiated by the fire, and we can see the fire through smoke. So we built a system combining cameras that work in those spectral ranges. We put it together and we've mounted it, we've flown it on a bunch of different aircraft with help of those collaborators that I was speaking about. So for example, here you have a NOAA airplane, NASA airplane, and a couple of helicopters that we've used in field experiments led by the US Forest Service. And here's what we can do with it. For example, this is the California Canyon Fire Experiment. This is an experiment we at San Jose State we coordinated with Greg Clemens and in collaboration with Wildfire. Wildfire basically burned a canyon, and we were able to record it and sample observe fire behavior, but also collect data about vegetation, meteorology, etc. So I hope the video is playing. There you go. If you see the video, you'll notice a quick acceleration of the fire inside the canyon. And this comes back to what I was mentioning. So in broad strokes, in general terms, everyone knows, if you ask any firefighter, everyone knows that fire accelerates in canyons, right? The question is how much, when, uh, how to predict it, what's the uncertainty on the velocity of the fire spread, those kind of things. We need to put numbers to them. And these technologies allowing us to quantify that fire spread. For example, here on the right, you have the isochrones that show how the fire progressed and when the fire was at different points in time. And with that, we can compute rates of spread, so the velocity of the fire. And we can also, because these cameras are radiometric, we can also estimate the energy released in the form of radiation by the fire, and that energy is related to the the amount of fuel that's consumed and the amount of energy that's released to the atmosphere. So it affects the other phenomena that are important to characterize. Now, to get here, it's not particularly easy. We have the technology now, but there are a bunch of challenges that we've had to overcome in recent years to produce these data. Here's an example from a different data set collected by Cruz et al. In Australia a few years ago. And here, what you can see is what comes out of the sensors as it comes out of them. If you mount a bunch of cameras on a helicopter, this is what you get. Now, to get from numbers and a nice quantitative characterization of fire behavior, there are a few data processing steps that need to happen. For example, one of the things we've done recently is develop video stabilization and automated georeferencing software so that we can, all that data that comes out from the sensors, we can put it on the map. Right, so you can see the raw video here on the left, the processed video on the right, and that software, those tools allow us to project all that information on a map, and that way we can cross-analyze it with vegetation data, weather data, etc., right, to produce knowledge that we can use to improve the models. In this regard, for example, we're extensively working with the US Forest Service because they are experts in measuring vegetation and fire effects on vegetation. So when we do a fire experiment like this, they usually come out to the field before and after the fire, and they measure the amount of vegetation that there is, the moisture, the distribution of the vegetation, etc., everything that may affect fire behavior. And then we cross-analyze that with the amount of energy released by the fire to see the correlations that there are between fire dynamics and the impact on the vegetation. Other people do the same for the soil, and this energy released by the fire is also an important input to those coupled fire atmospheric models. Well, things are relatively easy. They're not necessarily easy, but relatively during a fire experiment, when you know where the fire and when it's going to happen, right? Those are field experiments like the one I just showed. But we have a limitation in the size and intensity of the fire that we can generate on purpose, right? And so it's also very interesting from a scientific perspective to measure and observe uncontrolled large wildfires like this one here. This is a mosquito fire. It was the largest fire in California in 2022, and we had the opportunity to observe it from an airplane during the Cal Fire campaign. So on the left here, you can see the pyrocity that it put out. So it was we witnessed extreme fire behavior, and we had the opportunity to observe some of that using our IR cameras. What's the usefulness on that? Well, now, as I said, we can cross-analyze those measurements of fire temperature and fire radiance. We can relate that to, for example, wind velocity and the updrafts generated by the fire, because that's a very important phenomenon that's related to the generation of pyro-CVs, right? So everything at the end of the day comes together, but there is so much data that you need, so many observations that you need to make in a coordinated way, and you need to integrate them and geo-reference them and synchronize them. So it's not at all an easy task, and it requires a lot of people and a lot of effort and long planning. These things take multi-year planning before they happen. So that's kind of an overview of what we can do. I'm going back for a second just to summarize this. We're interested in observing how the fire spreads and how much energy it releases. Basically, those are the things we can do. And as Chris said, depending on the specific case, we may be more interested in spatial resolution or temporal resolution or spectral resolution. So in Swiss, we have two Telops cameras, one fast M150, that's a broadband mid-wave infrared camera that we use to quantify, for example, the fire radiative power, so the amount of energy released by the fire. And we've also recently acquired a multispectral camera, an MS100 HD, which allow us to get a little more detail on the different gases that are out there, and that's really the example that you saw earlier from WPI. Now, beyond our sensors and Telops cameras and things we can have full control of, we are also expanding what we can do because of how hard it is to gather this data. We don't want to restrict our research to having to deploy our sensors, which is a lot of fun, but we can only sample so many fires, right? So now we are collaborating with a lot of fire management agencies in the US, in Spain, in Australia, in Europe, to gather their data, because there are a lot of fire management agencies like Cal Fire that collect IR imagery as part of their routine tactical surveillance of the fire, because they want to know where the fire is and they track the fire. And to do that, they fly infrared cameras on their aircraft, right? So one of the things we've done recently, and Chris has led that, is we've processed some of those data that Cal Fire collected to also try to make it useful for science. And finally, to wrap it up, at the end of the day, what we want is to make all this data available and use it to improve models. So, and there are a lot of ways we can do that. So some work we've also done is related to data ingestion in models or data assimilation, and how we use all these observations to improve models. And we can do that offline, just tuning some model parameters, or we can also do it online in real time. If we have a model running and we were able to have these kind of observations in real time, we can feed the observations to the model to make the model improve its performance. And that's about it. I'm hoping that was not too fast, and I'm hoping we can have some time for questions.
Yeah, absolutely. Thank you for Miguel. That was a great presentation. It was a great overview of kind of what society is dealing with in fire right now, and how we need to go about improving and observing fire using remote sensing technology such as infrared cameras. Now, if I have some time for questions, if anybody has some questions, then go ahead and put them into the questions box over here, and we'll go ahead and take a look at them, try and answer them. Let's see, we do have one question. I will assign it to you, Miguel. So our first question from, could you discuss how satellite imaging and your airborne imaging complement each other, and or how your system is better than satellite imaging?
Great question. They do complement each other. I don't think one is better than the other. They're different. They provide different views of the same phenomena. And there are pros and cons to each of them, right? So, for example, airborne imagery provides a way better spatial resolution and much better temporal resolution. So if you want to see how a fire progresses with high temporal resolution, like the canyon experiment that I showed, then you need airborne imaging because satellites, polar orbiting satellites, which are the most useful for this, only allow you to see the same spot on Earth around twice a day. So you have 12 hours where you're blind, right? You only see the fire once every 12 hours. If you want better temporal resolution, airborne imaging is a great solution for that. You can mount your camera on a helicopter and you'll have continuous sampling of your fire. Now, airborne is challenging to deploy. So you need the sensors, you need the aircraft, you need the permits to fly the aircraft, you need the pilots. Like there's a huge infrastructure around it, and it's really hard to do it. And it has happened to us that it's really hard to put all that together. And when you have it ready to go, there may not be a useful fire to sample, right? So there's timing constraints. On the other hand, satellites are flying all the time, continuously. You have data from a lot of years back, and they provide a very nice global overview that allows assessing trends and maybe making projections about the future, more of a global studies. Yeah, so satellite products are definitely useful. There are a lot of there's a lot of research too on spaceborne sensors and some new initiatives where they are trying to improve the temporal and the spatial resolution of spaceborne sensors through larger constellations, for example. All that is very, very intriguing. Like it has a lot of potential as well. So let's see. Maybe someday we don't need to fly our own sensors if satellites get good enough.
All right. Thank you for that question. I will shoot you over another question here, Miguel. And this actually brings up a pretty good point in all imaging. The question is, Miguel, do you have issues with saturation?
That's a very good point.
Yeah, saturation is definitely a big topic within imaging. So this is a good question here.
Yep, who doesn't, right? If you want to sample fire, you have a cold background, a high intense fire, there's always these dynamic range discussions, right? Where if you, if you want to see the fire, then you may miss the background and the other way around, and that may end up in saturation. So it's always something you have to keep an eye out for. But you can adjust the sensors to prevent saturation. At least the sensors we use. Not every sensor in the market. Not with every sensor in the market you can allow saturation, but with some of them we can. Telops sensors in particular, we've been able to avoid saturation. Sometimes at the expense of not seeing the background or seeing fewer parts of the background. But yeah, there are ways around it. You can always adjust exposure times, etc. Add filters. Great point.
Great. Yeah. Yep. It's been an issue for a lot of people sometimes, but luckily we haven't had to deal with that a whole lot yet. Okay, I'm going to throw out there one question, kind of end on this question, could be a big question. Where do you see the future? Like, what do you see in the future for infrared imaging and studying fire behavior? Like, is there anything in particular you say, okay, this would be great if we had this, and this would help us improve fire behavior observations as far as infrared imaging goes or remote sensing? I know that's tough and it's kind of loaded, but
that's a tough one. It's worth discussing. Do we have another hour to discuss that?
Yeah. Or is there anything you see that you think would be useful to help fill some gaps, in a sense?
Well, it's just, I think we are on the right path, honestly. It's just we're making good progress. All this technology is allowing improvements. So now we have data that we didn't have 10 years ago. There are a lot of data processing issues along the way. So a lot of the problem or a lot of the challenges have to do with data standardization, building consistent data sets for the science community to use, that kind of thing. In terms of sensors, improving dynamic ranges is definitely a good point, but it's been dealt with. Improving the spectral resolution of the cameras. In a nutshell, we need better, lighter, cheaper cameras, if you can make them.
That would always be better.
Cheaper so that everyone can have them and share their data. We want them light so that we can fly them on drones. And we want them with like hyperspectral capabilities, very good spatial resolution, and like 100 hertz. That's my wish list.
It's yours. All right. Well, thank you for that. Thank you, Miguel, for joining on and presenting with us today. It's a great talk. And thank you for everybody who joined us today. We hope that you found the session informative and valuable. And, we appreciate your participation. We appreciate the questions that were sent in from the audience. If you have any further inquiries, please feel free to reach out to us. Again, a recording of the session will be available soon, and we'll also be sharing additional resources for those interested. We'll also provide the written responses to any other questions that we weren't able to get to. Thanks again for joining us today. We look forward to seeing you guys at our future webinars or conferences. We go out to conferences and events. If you see us, you see somebody walking around with a Telops or Exosens shirt, please feel free to stop, say hi, talk a little bit more if you want to. All right, everybody, enjoy the rest of your day, wherever you're chiming in from, and we will see you next time.
Thanks, everybody.